Hi, welcome to the very first webinar of the Energy and the Environment webinar series. I'm Kai Law. I'm the new head of Energy and Environment Research Division. Let me first explain a little bit about the motivation behind this seminar series. I guess this is really the response to the twin challenges. The first challenge is a pandemic, which has been around for some time. So over the past 1 year or so, we have been really, in a way, isolated. So I think there is a real need for intellectual space for us to connect with each other and to talk to each other and stimulate the intellectual activities while we're actually physically isolated. And also, I think it's very important for both, academic members and also PhD students, postdocs, all of us to come together and to, exchange views. It is our intention to have both interdisciplinary talks, cross-cutting talks, but also we're going to have some specialized talks that are probably targeting specific areas within the big umbrella of energy. Now, fortunately, this is a very big subject or big field, truly interdisciplinary. So I hope that both the cross-cutting and also specialized talks will be of interest to most of you. The second challenge we are targeting at is the climate change or the energy challenge. They're all together. So it is unfortunate that even during the pandemic, where lots of the activities are restricted, shut down, we still see, the signs of climate change from the, forest fires in California and Australia to the extreme weather in the UK. I remember last year we were talking about the hottest April or something like that, and this year we have the wettest May. So it's all kind of extreme. So while everything may be at a standstill, but the fact is that the past carbon emissions is actually acting upon the whole climate system. So there is no coincidence that actually this year or very recently, the International Energy Agency has created this new roadmap to net zero by 2050. So this is very ambitious, even from my point of view as someone who has been working in the energy field. It is extremely ambitious. How we're going to get there, it is a big question, but that's why we need actually the joint wisdom from all of us to actually meet that challenge. So hopefully our seminar, our webinar series will actually contribute to that. And the preparation has been long and actually quite a challenge too. I have to say, I really would thank Nelia here, who has really been behind this. There's enormous amount of background work done by her. So she will actually be the real host for this seminar series. But before that, before I hand over to Nelia, I want to say I'm extremely delighted that the first seminar will be given by our own people, and that is Helen. She's her work, of course, is very wide-ranging exactly in the cross-cutting areas of energy and environment. But following this, we're going to have 4 external speakers, in June and July, and then there's a long list of other speakers from around the world. Let's see. So one of the greatest advantage of this webinar series is that we can actually reach both speakers and also the audience all over the world, and that's exactly what we want to do. And we want the whole thing to be a joint effort, collaborative effort to meet the challenges we are facing now. So without wasting your time, I hand it over to Nelia.
Thank you, Kai. Welcome everyone to our energy and environment webinars. As Kai was saying, we are going to have today Helen Czerski, ocean physicist, who will be talking about how the oceans breathe. And so she will be talking about 30-40 minutes, and after that we will have a Q&A session for any queries that you would like to ask her. So all yours, Helen.
Thank you, Nelia, and thank you for asking me to start this webinar series off. So Nelia was correct. If you're into labels, one of the labels I have is ocean physicist. I'm basically a physicist studying the ocean in an engineering department, and that doesn't sound as bonkers as it seems, I think, because a lot of it comes down to fluid dynamics. And so I make no apology that today I'm basically going to be talking about oceanography, about the planet, and you'll see that aspects of engineering come into it, and that there are good reasons for having this perspective in an engineering department. And one of the things that is great, one of the first things I said to Kai when he took over the energy environment group was this idea that, well, we always talk about the energy, but we don't talk about the environment itself, and perhaps bringing in some aspects of how the environment would help us engineer things for the future. So that is what this is all going to be about. But of course, you all know me, and it's basically going to be about bubbles. So I'm going to share my screen, and hopefully you can all see a slide. And if you can't, tell us now, although I won't be able to see the chat screen, so you might have to tell Nelia or Kai. So this is what I'm going to be talking about: how the ocean breathes and why the bubbles matter. So here's what I'm going to talk about. There are lots of things. So there's basically 3 massive subjects here that I can talk about each of them for hours. I'm not going to. I'm going to give you a sort of flying overview of what's going on. And there are much more detailed things to say on all of these topics, but I want to present perspective to you now and some examples of the kind of data you get when you go seeking to answer these questions. So we're going to start off in the top left of this screen here with a bit about bubbles, but you can't really understand that without zooming out to Earth and ocean. So that will come next. And then the examples will come from 2 major field campaigns, one in the North Atlantic, which happened just before I came to UCL. So I got off the boat, and the next place I landed was my first day at UCL pretty much. And then also in the high Arctic, which means the North Pole. And then come back around to these questions. And the thesis of the whole thing really is that things like bubbles matter, and things like scaling is very difficult when you're dealing with complex systems. You can think of the Earth as an engine. It meets that definition if you consider an engine to be something that takes in heat energy and produces movement. But it's extremely complicated. We're used to a reductionist approach in science. That's got a long tradition. It's very useful, but we're dealing with a very, very complex system here. So a bit about the bubbles first, because just to set the context, because I know that lots of people study bubbles for lots of different reasons, and lots of you will be familiar with that kind of work. So the bubbles I'm talking about are generally between 5 microns and 5 millimeters in radius. The big ones and the small ones have different functions in the system, but they're both in there. They can last in the ocean from less than a second to several hours. And I've got data to prove that. And the things that they do, they're mostly formed in the open ocean. So we're not talking about breaking waves at a beach. We're talking about out in the middle of the vast expanses of the global ocean. When wind blows over the ocean, it pushes up waves. Eventually those waves break, which is the energy dump actually for the wind system. You know, the wind, the energy goes from the wind into kinetic energy of the ocean, the waves, and then eventually when waves break and to some extent are attenuated, that's your dump of that energy as heat energy into the ocean. So the picture on the bottom right here is slightly on the extreme side, but the light blue patches under the surface, those are the bubble plumes that you can see even in these conditions. So these are the bubbles we're talking about, the ones formed in storms under breaking waves, at least for the first bit here. And those bubbles have a lot of consequences for the air-sea system. So they are important for transferring gases between the ocean and the atmosphere in both directions. They also rise to the surface and burst, and these produce natural aerosols, and those can be salt, they can have organic matter in them. There's a very wide range of those, but they're very important for the way the atmosphere functions. And then the bubbles also change the ocean optical properties. You can see evidence of that from satellites as well as more locally, and they generate and scatter sound. So although bubbles are very small, in these conditions they come in very large numbers and they affect the environment. So just as an example of the sort of environment we're talking about, this is a video. I know it's probably a bit jerky for you. This is a video taken from the back of the ship in the middle of the North Atlantic. You can see, so you can't actually see how big this is. The average wave height in the way that oceanographers measure it was 10 meters at this point. So it's a big ship and you can't quite see the scale of it, but it's the wind was blowing 65 knots, which for those who like SI units is sort of 28 meters per second. And it was an extremely violent storm. It was actually what turned into the St. Jude storm when it hit the UK. So these are the conditions in the open ocean that produce the most bubbles. And what's actually happening here, even though you can't see it in the video, is that the ocean is taking a deep breath. So stormy conditions associated with the production of a lot of bubbles form a way for the ocean to breathe in. And here's the difficulty, is that the bubbles are like, well, you can see, you can look at a video, you can see the bubbles, that's great. The interesting processes are all happening in the top at most few meters. So the really interesting bits are in the top 10 centimeters, and then you're going down to perhaps 5 or 8 meters depth. The entire surface of the ocean can be going up and down by more than that. So although seafarers have looked out at stormy seas like this for centuries, the detail of what's going on just underneath the surface is still quite a lot of a mystery, and those are the bubbles that I'm interested in. So you might ask yourself, that looks like a horrible big storm. It obviously takes a big ship to get there. It's, you know, you have to go for a long period. It's very difficult to do anything because everything's moving about a lot. Why would you bother? What idiot wants to do this? And the answer comes in taking a bigger picture of why these bubbles matter. So we're going to move on to the relationship of the ocean to the Earth system. This is a very famous photograph. It was taken by Bill Anders on Apollo 8. Apollo 11 was the one where they landed on the moon for the first time. So on Apollo 8, they orbited the moon, and this was on about the 3rd or 4th orbit. And Bill Anders got out his camera and took this photograph across the top of the lunar landscape, looking back at Earth. And it was one of those photos that changed human perception of itself, possibly more than any other photo in the history of civilization up to that point. Although obviously photos hadn't existed, you could make it image, any other image in the history of civilization. And when you look back at Earth, when the Apollo astronauts looked back at Earth, what they saw was the Earth, but what they really saw was the ocean. Our planet is absolutely defined by its ocean. You all know the stats, you know, it covers 70% of the Earth's surface. On average, it's 4 kilometers deep, but basically it's a massive reservoir of water. Water that's got a very high heat capacity, that is liquid, so it's in its middle phase at the temperatures we're used to. And the ocean absolutely defines the way the entire Earth system works. So it's really like, there's a reason we're called the blue planet. And obviously it gets my goat that we don't appreciate the blue more. There's a whole other talk about that. So here's the point that's relevant here, is that there are 2 massive reservoirs that operate on short timescales on our planet. The land people might get a bit upset about that, but I'm sticking to my 2. And they're the atmosphere and the ocean. So they are sort of similar in extent, but they're very different in the sorts of things they do. So we hear a lot about carbon. Kai was talking about climate change. the ocean holds more carbon than the atmosphere by about a factor of 50. So the reservoir, the buffer for the system is the ocean. That's not to say what's in the atmosphere isn't important, because obviously it changes the radiative properties of the atmosphere. And in addition with the other greenhouse gases like water keep the planet warm. Carbon dioxide is an extra greenhouse gas that changes the energy balance. So basically the same amount of energy, more or less, arrives from the sun, but the extra carbon dioxide in the atmosphere slows down the rate at which it leaves. And so before you had two big numbers that were balanced. And now what we have is two big numbers that is, and one of them, the rate of energy leaving, has slowed down a little bit. And so energy is accumulating on Earth, and that is what climate change is. And we know, because we can now measure it directly, that 93% of all that extra energy that accumulates on planet Earth is in the oceans. It's in our reservoir for heat. And the reason, the thing that matters really, along with all of that, is where it is, because the ocean is not just one big pond. Things move around it, it's very large. If anything gets carried down to the depths in the ocean, it's basically locked away from the surface for a long time. But if it stays at the surface, it can obviously exchange with the atmospheric reservoir. So in the questions of how what is climate change and how it works and what will happen in the future, this I think is a very useful framing to understand that these are reservoirs and they hold things, and the system depends on them having the amount of stuff like carbon and energy that they have now. And when it comes to the exchanges between the atmosphere and the ocean that I'm going to talk about today, there are basically three main ones. There are some others. There's carbon dioxide, there's oxygen, and there are particles. So let's have a look at what it looks like when the ocean acts as a reservoir. So what we're looking at here is it's a map of the Earth, obviously, and the colours show you how the ocean is breathing. And this is an average over the year for the year 2000. So the red colours, those are places where carbon dioxide is coming out of the ocean. The ocean is on average breathing out. And you can see they're clustered around the equator, the intertropical convergence zone off South America. And then in the mid-latitudes, there's a bit less going on. And then once we get to the more northern latitudes, you get these pink regions. So you can see there's one in the North Pacific, and then there's a bigger one up here in the North Atlantic. And these are places where the ocean is breathing in. And that's a surface thing. Carbon dioxide is being taken in on average at the surface. And the reason that this region matters so much, the one that's got the black circle around it, which is the top of the North Atlantic and the Labrador Sea, is that this is also a place where water gets taken down. You have deep water formation. So any carbon dioxide that gets taken up there is likely to be shunted down into the deep ocean and not come back for 1,000 years. Whereas in the North Pacific, you can see off Japan in the Kuroshio, there's a lot of uptake, but there's no deep water formation. So it's not just about the fluxes at the surface when it comes to carbon dioxide uptake or oxygen uptake. It's about where it gets transported after that. So all this is about budgeting fundamentally. It's an accounting system for a planet, and carbon dioxide is coming and going in different ways in different places. So there's a pattern. So then you might ask, well, what have bubbles got to do with any of this? So here's the headline version. So we have a breaking wave that's there because a lot of wind blew, pushed up waves that became unstable, and they broke. Traps a load of bubbles underneath it, and then some things happen quite quickly. So bigger bubbles will rise to the surface within a few seconds and basically pop and disappear. Any tiny bubbles that are left will get carried downwards, and you'll see later this is a bit of a simplistic model, but more or less it goes something like this. Now, what we understand is that it seems to be, because carbon dioxide is weakly soluble, relatively soluble on the scale of ocean gases, it's the bigger bubbles at the top which appear to be more important for carbon dioxide. So it's obvious that a bubble's a packet of the atmosphere carried down into the ocean. But the reason that there's an asymmetry, the reason the bubbles matter so much is that obviously as you go down underneath the water, you have extra pressure. So you're pushing the gas out into the ocean, and the deeper you go, the greater the push. So there's this, so if you generate some bubbles, you're already squeezing, you can easily squeeze gas into the ocean that wouldn't have got there, because you can make the water supersaturated. And then surface bubbles, it's not actually the very deep ones, rise to the surface, and you get white caps, which are these patches of white foam on the ocean. And when they burst, they spit particles up into the atmosphere. And that is important because a lot of the chemistry in the ocean is very good at changing the way that clouds form. So you can see here the major ways in which bubbles affect you know, what's coming and going across the ocean surface, which is the big question here. There's an obvious way for gas to get into the ocean, and there's an obvious way for particles to be produced. So all of this is going on. So that's the simple headline version. So this is why the bubbles are related to the carbon dioxide. It's because the breaking waves and bubbles, we can see in high winds, they are driving the uptake of carbon dioxide. But it's not clear how much it happens because the measurements are all over the place. You know, we know that in high winds, more carbon dioxide gets taken up, but the variation is huge. And we don't understand the processes that make it bigger in some conditions than others. So there's a lot of process understanding that we don't have at the moment. And when it comes to the really big questions, you know, this plot on the right is really important. I think it shows this really nicely, that what you can see is carbon dioxide concentration, carbon, let's say. And on the left-hand side, you can see that in 1870, there was about 288 parts per million in the atmosphere. And then we burnt some coal, and we burnt some oil, and we burnt some gas. And there was, we changed our land use, which took up, which produced carbon. And then on the other side, you can see where it's all gone. And you can see that the land took some back. A lot of it is still in the atmosphere, but about a third of all the extra carbon dioxide that we as humans have emitted since the start of the Industrial Revolution has gone into the ocean. The ocean is doing us a massive favor, because if it wasn't taking up that, it would be way past the Paris climate targets already. We'd be in far more trouble. Now, that carbon in the ocean is not without consequences, but that's where it is. So the first big question is, you know, whatever we do, despite our best efforts, we're going to keep emitting carbon. Is the ocean going to keep doing us this favor as climate change changes the patterns and the storm systems and the way the system works? And then the next question is, how much of the gas that is taken in at the surface is exported to the deep ocean? And will that change if the way the Earth engine moves, if that's changed by climate change? And then, you know, so you're asking about how the ocean breathes, and then you get back down to these, which mechanisms are producing and destroying bubbles, and how exactly do these bubbles influence the gases and the particles, because they are right in there at the interface between these two massive reservoirs. So they're really important. So I've just realized I can't see. Oh, here we go. Okay, so I can see what time it is. That'd be a useful thing. So we're going to come to the first example of how you start to answer some of these questions. How do you cross the scales? Because we've got a question here which is planetary in extent, and the processes driving it happen in milliseconds and quite often on scales of smaller than a millimeter, and they're not easily scalable. So the game here is linking across the scales in a real system, which is very complicated. So this was the expedition that the Stormy Seas video came from before. It's called High Wings. And we were up in the sort of top left corner of the North Atlantic, as you're looking at the globe there, sort of just off about 500 miles south of Greenland, bobbing around there. You'll notice that that is pretty much right on the storm track that crosses the North Atlantic Ocean. So the jet stream that brings Britain its weather, you get storms formed along the jet stream connected to it, and they are carried from west to east across the Atlantic Ocean. And so we parked ourselves just south of Greenland, and we sat in the middle of storms arriving for 6 weeks. So we didn't see many other people there. There were not many other people. My bit of it, so we were in that region there. So my bit of it, so there's this terrible thing, right? It's not me. All the other ocean scientists and earth scientists in general have this horrible habit with acronyms. And so my bit of it, this is my colleague's idea: turbulent exchange of aerosols, bubbles and gases, technically TBAG, which was lovely. So what do you do if you're in the middle of a massive, great big storm and you want to know about bubbles that are a few meters beneath the surface? This is what I did. And this type of experiment, so this is a spar buoy. It's basically a giant yellow stick, 11 meters long, floats upright in the water, got instruments strapped all the way down it. And it's actually really hard to get to the point where you get something like this in the ocean. There's very few occasions when this has been done, especially actually in the past 10 to 20 years. There was a bit of a fashion for doing it before that. So the way this works is or the way it worked for me was that the ship is sitting there in the middle of the ocean getting hit by storms, but you have a quiet period in between. So in the quiet period, you can bung something over the side. And this was the buoy here. I call them buoys because I learned my oceanography in America, and because apparently it's wrong to throw buoys off the back of ships. So the instruments here, so this was the thing, this bubble camera, this is only the third one that's ever been built. I designed it along with a colleague at Southampton University, and it was designed for this experiment. It measures bubbles. It's quite hard to photograph bubbles, so you can measure them well, but it was designed to do that in these stormy conditions. So it can measure bubbles from 20 microns to anything up to 4 millimeters in radius. And it can sit out a storm and just measure bubbles continuously, basically. A bit further down the hull here, we've got acoustical resonators. So acoustics is a really useful way to spy on bubbles because they are compressible. So they turn an mostly incompressible fluid into a compressible fluid. They're resonant at certain frequencies. You can learn a lot with acoustics. And then down the bottom, you can't see it really clearly, but there was a sonar, which was looking up at the surface. So the advantage of this experiment is that, first of all, we were in quite nasty conditions. This whole apparatus could float freely for days at a time, and it could get detailed things like bubble size distributions from different places. But at the same time, the sonar could see everything. So this is a kind of schematic of this thing in the water. You can orient buoys, so the wind and the waves, if they were coming from the right, moving across to the left, the buoy would basically always face them to within a few degrees because of the mass hanging off the bottom. So all of the instruments were on the front side, apart from the ADV, which is measures velocity, water velocity in 3 dimensions, which was better off where it was. So I've got bubble size distributions going down the hull. The sonar was looking up and out in a sheet, so it could see the waves and the bubble plumes that were oncoming. And there were various other bits and pieces on that, and also a camera looking down from the top to see foam patches on the surface. So this thing produced vast quantities of really interesting data, and I haven't got time to tell you all about it. But I'm going to tell you about three things that are just examples of the kind of things that you can learn if you have that sort of equipment. So there's a lot of bubble size distributions in my life. So the plot here has bubble radius on the bottom. So about halfway is 1 millimeter. And then it goes from, 10 microns up to centimeters. So the number down the side is this thing that bubble sign, you don't need to worry about this very much, but it's bubble number per unit volume per micron radius increment, which is a commonly used way of doing it. The important thing here really isn't any of the details. The important thing is that bubble size distributions have a very specific shape in the ocean, and they tend to stay that way. So if you look at the 2 black lines, the black line that isn't dotted, that is someone else's data from right inside a breaking wave. And it's considered that those are bubbles just as they've formed. That's what you get when a wave breaks before anything happens to those bubbles. And then the dotted line shows that same population a few seconds later. So the big bubbles have risen out, perhaps some bubbles have shrunk. We don't honestly know an awful lot about how all of that works. But the size distribution, the bubbles there rise out, the population shrinks for several different reasons. And then the colors on the left are data from this expedition. And, you can see, so the numbers on the right are void fraction. So a void fraction of 10 to the minus 4, for example, means that of that square cubic meter of water, 10 to the minus 4 of it is gas. So it's a useful headline figure. It doesn't give you the size distribution, but it tells you how much of it is gas. And you can see that as the plumes fade away, if you like, there's a debate about how exactly they disappear, the bubbles shrink, but the bubble size distributions are really consistent. It's not like you get some big bubbles and some small bubbles. The populations keep to these sizes and they shrink in a very consistent way. So you can really dig into the details of all of this, and I have. And then just, as an example of something else you can get, one of the things that I found from this expedition is that basically whatever the conditions are, the void fraction, the total amount of gas in a cubic meter, never goes above a certain value. It doesn't matter how nasty the conditions are. And we were in big storms. never goes above 10 to the minus 4.5 approximately, which is quite important if you're a bubble person because of the history of this field. So what you can see on the plot here is log 10 of the void fraction at the bottom, and normalized probability, and the colors are wind speed. So this is why we're asking the question, because as the wind speed goes up, we know the ocean is doing more breathing. We know there are more breaking waves and there are more bubbles formed. So the question is, what does that do to the plumes at 2 meters depth? And you can see that at the lowest wind speeds, the bubbles, in fact, the few lowest wind speeds, the bubbles pretty much always have the same void fraction, which is interesting all by itself. But if you really push it to very, very high winds, then you find that even in those conditions in that video I showed at the start, the void fraction is never higher than this limit. It's like the distribution just kind of becomes squished up. So more bubbles than that never get taken down to these depths, which is interesting if you're asking these questions about bubbles coming and going across the surface. And I'm just going to show you, so basically the story of this expedition, and there's a whole separate research talk on this, is picking apart these details. What are the bubbles doing? Because I had an advantage that no one else had up to that point, which was that I had a sonar looking at the whole picture, as well as detailed bubble size distributions inside what it could see. And that's a very useful thing. And just as an example of how useful that is, so you get deep plumes formed underneath breaking waves, and they're squished over to one side. So the plot here shows the yellow bits at the top, that's the sea surface. So it's a sonar. It's a stripe on the sonar, so you're watching the sea surface as it goes past the buoy. So the wiggly bit at the top, those are just normal waves on the ocean. The sort of spotty bits below the yellow wiggly line, those are bubble plumes, and this is matched up with the previous figure. So the wind is coming from the right to the left, and you can see that the bubble plumes are sheared, and that's because of Stokes drift, because waves are, the rotational movement of waves varies with depth. But the important thing is that it turns out that if you have the bubble measurement devices that I did, you can actually see, you can measure how sheared, how much that the bubble plume is squished over. And the reason that's useful is because it lets you get at the age. You can look at the conditions, you can work out what the shearing process is expected to be, and that means you can kind of wind time backwards if you're assuming the plume started vertical, and there are good reasons for thinking that, and actually work out how old these deep plumes are, which no one had done before. And it turns out that approximately 10 minutes, they don't tend to be older than 10 minutes, which is really interesting if you're considering fluxes, because you can only measure presence, but if you have an age, then you can start getting at fluxes. So anyway, so a lot of my time is spent picking apart details of what's happening underneath these breaking waves in order to inform the breathing processes. But the bubbles are right in there for how important those processes are. And I'm going to skip over this, but just look at the pictures on the left-hand side here. This is pretty much the process, that waves break at the top. You have actually a shallow plume, which is separate. Some of those bubbles, only some of them, get carried down into the deep plumes. The deep plumes shear, and then the bubbles are destroyed. And so we're starting to pick apart the breathing process, but it's very hard to get out there in the middle of it. So, but perhaps in comparison with some other areas of science, perhaps it's moving quite slowly, but that's all we've got. It's hard to get a ship out to sea. But I want to move on. So that's an example of bubbles in changing things in the ocean in big storms. So I want to move on to the next field expedition. Again, there's a huge great research talk on this, and I'm just going to skim over the surface. And this, so you can see the Labrador Sea, the North Atlantic, where the previous expedition was, that I talked about, is in the bottom right of this picture of the globe. And now we're moving right up to the middle of pretty much the middle of the Arctic Ocean, where the North Pole is. You can see the ice here. We've got Greenland and the Canadian islands on the the lower side of the globe, you can see this is the Arctic in summer. So you can see it's mostly ice-free these days on the Russian side and across the Chukchi Sea. And there's thicker ice in Greenland. But even in the summer, you have this patch of ice. And the Arctic Ocean, because of that patch of ice, basically works differently to any other ocean. But it's really important in how the ocean engine works. So it's not just this kind of ice-filled weirdness on top of the world. It's a really important component in the whole ocean engine. And the fact that it's distinctive, it's a different kind of ocean, it's a different kind of engine, is really important for how the rest of the global ocean works. So this was not my idea either. This cruise also got an acronym, Multi-Disciplinary Observatory of Cloud Coupling in the High Arctic. And as you've probably spotted, it was called MOCA. Sometime might have lovely colleagues, but really, anyway. So this was 3 years ago. I'm sure some of you will remember me going off to do this. And we spent 2 months on an icebreaker, basically at the North Pole. It wasn't actually the end point. It's just that we were looking for a certain type of situation and we kept going till we found it. And that was pretty much at the North Pole. That's where we started. And then we drifted after that. So the North Pole in summertime, before we get to the bubbles, this is what it looks like. It is not the case that in summer, these central Arctic regions are completely frozen solid. All this is sea ice. It was frozen ocean water. And so you get these big flat plates. There are no icebergs because there aren't any glaciers nearby, although we did see one, which was highly unusual. And you can see, so these plates, this big ice flow you're looking at here was about 2 meters thick on average. The really important bit, as far as we're concerned, are these gaps where there's open water between the bits of ice. So part of the reason there are gaps is that the wind is pushing the ice around all of the time. So it's always, everything is always moving. It's a bit like an ambush predator, that you never see it moving, but you turn around and look back and it's somewhere else. And it really is like that. It's kind of moving very slowly and very quickly at the same time. But these open patches of ocean, these are important because obviously they're the places where the atmosphere touches the ocean. So these are called leads, and they're open leads when they're looking like this. Over here, we've got the ship. So what we did for these 2 months is we moored our ship up against the edge of the ice flow. And basically that was our base. The ship was occasionally turned around to point into the wind for atmospheric measurement reasons. But we sat there, that was the base. And we just drifted with this ice flow for the whole time we were there. It's about 1 kilometer across. All these light blue bits on the surface, those are melt ponds. That's because it's summer. So the water that's frozen solid melts in the sunshine and then refreezes in the winter. And this was my walk to work, more or less, every morning. And I was working in this little bit of the open lead, which is up on the top left here. So it's quite a production, clearly, to get here, to be in this environment, to sit in the middle of this massive landscape, and then just to watch all of it. And that's what we were doing. This was the icebreaker, a Swedish ship. Does routine operations in the Baltic most of the year, but in the summer, when there's no ice in the Baltic, she does science operations in the Arctic. And there were loads of different people. There were atmospheric scientists. You can see there's 2 balloons here for flying experiments to look at what was inside the clouds. There was a whole range of gas transfer and meteorological measurements. There were biologists. There were people studying the ice flow itself. So it's basically a massive collection of everybody on this ship. And the reason that we were all there, the bubbles are about to arrive, don't worry, is that here we've got the situation that I discussed before. So we've got thin-ish plates of ice, a few meters at most, separating the atmosphere and the ocean with these open patches. There are little bits of life because in the summer you have 24-hour daylight. So there's little bits of life. And there are clouds above. Now, the clouds matter because this region is basically sending out long-wave radiation into space. It's a sink for Earth's energy. Earth's energy arrives from the sun as radiation, gets shunted around the Earth system, and then it's radiated away into space. And more of it is radiated away from the poles than you would expect. So the entire ocean engine is moving energy from the equator towards the poles, and then it gets radiated away as long-wave radiation. And clouds will stop that long-wave radiation. So if you want to understand the energy budget of the planet, you need to understand this energy sink, if you like, how much energy gets radiated away at the poles, because it's really important. And it depends on the clouds. And the clouds are a bit weird because every cloud droplet has to have a nucleus at the center of it. And there are very few particles in the Arctic. So here, you know, wherever you are at the moment, it's likely that you're breathing in air which has many thousands. So maybe 10 or 20,000 particles in every square centimeter. They're very small. Most of them are natural. Pollution obviously increases that. So 10 or 20,000 particles per cubic centimeter is what you would expect here, for example, wherever your here is. Up where we were, that number per cubic centimeter was 2 quite a lot of the time. So you're talking about tiny numbers of particles. So the clouds don't have anything to nucleate on. And so the question is, where do the cloud condensation nuclei come from and the ice nuclei? And the thing that is important is that they appear to come from the biology in the ocean. Something is transporting organic molecules from the ocean up into the atmosphere, and that's affecting the clouds. So that was a very quick potted history of the Arctic energy budget, but that's more or less the sequence. You need to know what's crossing the air-sea interface, because some of it is affecting really sensitive Arctic clouds, which affect the energy budget of the entire planet. So here's the thing. On the previous expedition, 10 years before, someone had seen bubbles in the leads. And if bubbles rise to the surface, they can pop. And if they pop and they're coated with organic stuff, they can spit that into the atmosphere. So again, there's another whole research talk on all the details here, but the reason the bubbles appear to be important here is that they might be spitting particles into the atmosphere. And this is a very different environment. All those big flat bits of ice mean that there are no breaking waves. The winds are generally much lower. The condition is very different, and yet there are bubbles there, and maybe they're contributing to all of this. So these are the questions. Were there bubbles? Why were they there? And if they are there, do they matter? Because, and all of those are different questions, interesting for different reasons in their own right. So this is I'm going to zoom through this bit quite quickly. This is the headline of what was going on. I had my bubble camera sitting just beneath the surface, looking for bubbles as the ice moved. I have a colleague, Matt Salter, who is an aerosol expert, who made a sort of trap for aerosols over the top. So we could measure the bubbles down below, and we could measure anything that was spat out. And, you know, we made lots of other measurements. This is Matt in our little hut that we had out on the ice to have lunch in, not heated, but still very sheltered. And the reason he's holding sieves is because sieves are one of the most useful things you can have in the high Arctic. If you ever go, take a sieve as a way to get slushy ice from one place to another. They are absolutely amazing. So yes, sieves, that's my top tip of the day. And then the bubble camera got a new home. So this was built by Phil Jevons in the Mechanical Engineering Department workshop, and I'm not making this up, everybody on the ship was so impressed by this little sledge thing. It could go in the water, so it could float, hold the camera at the right angle. I could use it, I could tow, that's me at the bottom right, I could tow it across the ice to move the camera around. It was a fabulous little piece of engineering, actually, that frame. It got the camera to where it needed to be. And so the camera could just sit out, float just below the surface, and measure whatever bubbles were going past. So again, I'm going to skim over the results, but just to give you just a picture of what was going on. There were a lot of bubbles, actually, far more than I was expecting. The void fraction is on, so we've got the date at the bottom. So this is covering the whole period we were there. The void fraction at the side, if you remember the void fraction from before, the most intense bubble plumes in massive storms in the ocean got up to 10 to the minus 4.5 as a void fraction. Here it went higher than that, and there's no breaking waves here. The assumption is that these are supersaturation bubbles, but they were really varied over 4 orders of magnitude as the ice shifted, and nothing on the surface was obviously generating bubbles or changing any of this. So there's lots of questions to ask here. And just as an example of how they were different to bubbles in the ocean, they were weird. So on the bottom here, we've got time. So this is one particular day going from 2:15 in the afternoon till about 3 o'clock. What's going up the left-hand axis here is the radius of the bubbles in microns, and this is by volume. So this is the volume of the bubbles at that radius. And what you can see is that over the 45-minute period here, there were separate populations, very narrow bubble populations that were shifting in size, and this definitely wasn't bubbles stuck to the lens. So these narrow populations were coming and going. It wasn't always like that, but they were really striking because they were exactly the same size. I've never seen anything like this. But obviously that's very interesting when it comes to how supersaturation conditions are affecting bubbles and fluxes of other things. So that was fun. And I'm still digging into that data. So that's, you know, there are still a lot of questions. You don't get to do expeditions like this very often. As soon as you come back, you wish you'd done a whole load of other things because you know better when you come back. But these questions are still, you know, I've got some answers. I don't have all of the answers. The question of why the bubbles are there is still not entirely clear. Like, what processes are happening under the ice to generate bubbles? And then there were some bubbles from splashing against the ice edge, which no one had expected. And it may be they're more important than all the tiny small bubbles I was looking at. But really, the thing that this all comes down to is that there are big questions about the way that the Arctic works now because it's such a distinctive part of the ocean engine. We know it's changing, and that means if we don't look at what it's doing now, we won't really understand what it's going to do in the future. And there are two big threats. One of them is obviously just that you remove that lid of ice, you remove the way the whole engine works. The other thing is ship emissions. As people are talking about crossing the Arctic in ships, you know, you can't go there at the moment unless you've got an icebreaker, but as the ice melts, then perhaps an ice strengthened hull escorted by an icebreaker could get through. Those ship emissions are really change the clouds, even if they're burning what's supposed to be clean fuel. And on the ship, for example, you could tell which way the wind was blowing because you could never see your breath, right? You could breathe out, it would be -14, you could breathe out, you could never see your breath because there's nothing for the particles to condense onto. If you were downwind of the ship, you could see your breath. And that was a ship with its engine switched off. Most of its engine switched off. So that the particulates from ships are really going to have a big influence on this very delicate system. So I'm getting towards the end of my time here. So just to get back to the big questions of the bubbles, this ocean reservoir is important, and it depends on two things. It depends on interfaces, the places where gases, trace chemicals, energy are exchanged with the atmosphere mostly, and via that with the land. So interfaces matter, and bubbles are right in there at the biggest interface the ocean has. And then internal transport is important. What are the flow processes inside the ocean that are making it harder or easier for these exchanges to happen? Where is this reservoir storing stuff? Because, you know, if it stores it somewhere it's not going to get out again, that could be quite different to a storage somewhere which is very accessible to other reservoirs. And so the bubbles are in there as an important part of all of these questions, even though they're very small and fleeting, that they are changing the interface, and it changes the way things happen because the interface is so important. So we can't currently parameterize their effects very well, but more importantly, because the mechanistic understanding is still poor, because it's hard to get to these places and measure things directly, it makes predictions about changed conditions harder. So if you don't understand the mechanism, it's hard to say what will happen in a warmer world, what will happen in an ice-free Arctic, what will happen next. And so the mechanistic understanding is critical. And obviously with the Arctic, the clock is ticking. So to answer all of this, you know, the hard bit is having non-invasive sensors. You can't measure bubbles if you're putting something in the water that generates bubbles. You have to make in situ measurements very carefully. So yeah, in situ measurement is always the critical thing. And I'm fortunate in that the camera and the resonators that I have, those are rare pieces of equipment. So I've got the kit to do it. I just need access to the ocean. And it looks like I'll be going back to the Labrador Sea in a couple of years. So planning for that is underway. I didn't talk about surfactants and particulates, but they stabilize bubbles, they change interfacial transfer. Surfactants in the ocean are really hard. There's a load of gels and polymers, and biology is really complicated. And there's a lot of big questions about the effects of surfactants. And then these larger scale transport processes, no one's ever really linked those two things together specifically, but I think that the flow processes are directly relevant to the flux questions, and they need to be studied at the same time, which has not generally been done. And of course, so oceanography, ocean science, we are a data poor science. Whatever satellites there are, anyone dealing with the inner ocean is data poor. We don't have enough. We don't have enough to know what's going on. We're piecing together fragments. And obviously what we want is simultaneous measurements of everything. What life was nearby, how much photosynthesis was going on, what stage were algal blooms at, you know, what was the upwelling and downwelling radiation. We want to know everything, and it's very hard to get at. So that's all of that. So yeah, so that's all I've got to say. And just before I finish, in case any of you were still thinking that measuring in these conditions is, we should be able to answer these questions, I want to show you this. So our friend here, the walrus, popped up one day while we were having lunch. There are not supposed to be any walruses in the Central Arctic. They're coastal animals. This one was quite fat, so it's clearly doing quite well, possibly the first one ever to have been seen at the North Pole. And one of the reasons that so Phil Jevons didn't have to design something for what was going to happen next, but these are harsh conditions. So the walrus, after it had a bit of a nose at that other piece of equipment, oops, oh, my mouse has vanished, here we go. So it popped up by some other pieces of equipment. That is a buoy for measuring carbon dioxide. There's the aerosol chambers behind it. Here's the walrus. It's probably never seen anything orange in its life. It's certainly never seen a buoy to do this. It knows exactly what it wants to do about it. And so the problem if you're designing things to come into these situations is that you don't really know. The conditions are still very difficult. Can you imagine? It fortunately didn't impale itself on that buoy. But I'm really happy we didn't have an angry walrus thrashing about with a tusk stuck through a buoy, because yes, that would have caused a few problems. So anyway, so that's it. And I'm happy to take any questions that anyone's got.
Thank you very much for a very illustrative talk, Helen. Has been very, very good. We have some questions coming in the chat. The first one is, how will this data from the expeditions help potentially to create a solution to slow down the climate change and global warming?
So here's the thing that engineers never want to hear, and it's a hard thing. It's that the ocean system is really complicated. The ocean, atmosphere, land system is really complicated, and we don't understand how all of it works. And we're changing it before we understand what it's doing. So there's always two stages to a process of doing something about climate change. One of them is reducing the damage that we're doing, that we know we're doing. But the other one is just understanding the system. And so a lot of this is directly at the level of understanding the system before we meddle with it. Because there is a tendency of engineers to say, oh, we're just going to do a thing, like we're just going to scoop all the plastic bits out of the ocean, forgetting that all the life in the ocean is at the same scale as the plastic bits. So you basically, scoop out all the life in the ocean. So this is at the level of understanding, but also the level of prediction, because if we want weather and climate models to work in the future, to be able to prepare us for whatever future is coming, we need weather and climate models that work, and that has to be based on mechanistic understanding. So a lot of this comes into that question of how do governments plan for the future. None of this is directly going to inform efforts that stop climate change, except that I think appreciation of how complicated this system is and how finely balanced it is actually, it's a humbling thing for humans. And I think that there tends to be this assumption, oh, we are humans, we can do whatever we want, and sort of we're in control. And actually this system is far more complicated than that. And it's far better to stop putting extra carbon into the atmosphere than it is to do any kind of mitigation whatsoever. So I think it's an appreciation of our place in the system. But we also, if we want to make predictions, we have to understand how the system works.
Yeah, it's more how we are damaging and creating the worst conditions. Another question, it is well known that you can use the piezoelectric effect to generate microbubbles. This is a bit technical, which great for cleaning. So if they are asking if the 5 micron bubbles act like this on chips, hulls, or does goes to the ocean pollution?
Oh, so cleaning things. So there are two. So basically, microbubbles are useful for cleaning if you generate them in a certain way. So my postdoc lab Tim Layton and that crew came up with a system for using bubbles for cleaning. You have to apply. It's not that microbubbles in general are great for cleaning. I think you have to generate them and apply them in a certain way. So there's a separate. So they are great for cleaning because of the way that they collapse. The ship hull thing is slightly different. So penguins do this. When if you've ever watched a penguin before it goes swimming, it will fluff up its feathers and store gas underneath its feathers, dive down to go swimming. On its way back up, it will release the gas and it coats itself with a coating of bubbles that reduces the drag by what is estimated to be 50%. And so people have tried imitating this for a ship hull to reduce drag around ships. Mitsubishi had a quarter scale model not so long ago. They never let me see it, so it's all very top secret, but the idea is that ship hulls, if you generate bubbles at the front of the ship and they stream along the back of the ship, you can reduce drag, and obviously that's an easy way to reduce fuel use. So the bubbles themselves won't contribute to ocean pollution. Bubbles don't last very long in the ocean, and microplastics are really dilute. So it always gets difficult at this point, because in our everyday lives, we have one idea of what dilute is, but dilute in the ocean means something else. So microplastics in the ocean, the very small bits, they exist at various depths. You know, the wind mixes them down, they stay up to the top, they get fragmented by UV. They're still quite dilute, but then all life in the ocean is dilute. So there aren't enough microplastics around to change the bubbles. We have done some studies on whether microplastics could stick to a bubble and be spat upwards. No one's ever seen it happen, because you have to have a piece that's very small, and by that point it would be biofouled. So basically life in the ocean uses plastic as a substrate to grow on. And so the biofouling changes the way those particles behave. So the microplastics themselves are not going to directly affect the bubbles. At the moment, it seems the bubbles don't spit them upwards. They do spit lots of other, I mean, I've got a PhD student working on bacteria, which can be spat out as the bubble bursts, but that process is quite violent. It tends to smash up any cells that are there. So the microplastics are not directly affecting these fluxes we're talking about. The reason they're a problem is that animals ingest them, sometimes because they're biofoul, sometimes because ocean animals don't have taste. They, the filter feeders in the ocean just filter everything. They just assume it's organic matter. So plastics cause problems for those reasons. They're not directly affecting carbon fluxes. Sorry, I can talk about plastics for a long time, but that's a separate question, separate issue.
I have a question of my own, actually. Do you think, because when you were saying about that you don't really understand where those bubbles in the North Pole are coming from, could it be from the biology breathing, or could it be also from because of global warming? Now the oceans are releasing the bubbles that were there captured long time ago.
So you're right that there's two things. There's a few possible reasons. So the ocean does off-gas. That's why it's outgassing at the equator, because there's warmer water. The water at the North Pole, because there's ice nearby, is basically always at exactly the same temperature. So it's minus 1.7 degrees Celsius, minus 1.68, because the ice keeps it, like if a bit more energy goes into the system, it melts the ice. Mm-hmm. So the ice covering the water covering the Arctic Ocean, the surface water is always minus 1.7 or minus 1.68 degrees Celsius. It doesn't, while the ice is there, it's not actually heating up. So at least you don't have off-gassing due to that. But what you do have is, so you're right about the two other effects. There's basically two candidate mechanisms. One of them is that there's a question about whether they're oxygen bubbles. I had an oxygen sensor that didn't work, but it seems that the bubbles were more likely when there was oxygen produced, when there was high levels of oxygen in the water. What we don't have is data that separates oxygen from nitrogen. So it's quite hard to get sensors for nitrogen, accurate ones. So what you really want is the ratio of oxygen to nitrogen, because then you know whether it's biogenic oxygen, whether it's come from photosynthesis, because the ratio will be higher than it is in the atmosphere. The other possibility, though, so it might be that there's life below which is generating an oxygen supersaturation because it's photosynthesizing. The other possibility, though, is that gas is taken up in equilibrium and then things change and there's mixing, because the water below, so I said the temperature is the same, the water below can be a slightly different temperature, and the ice is very dynamic. And so you could get pockets where it was locally supersaturated because of mixing processes. And so it might be supersaturation generated for that reason. And one of the many things that I didn't do that in retrospect I would like to have done, so that somebody, not me, dug a big hole in the middle of the ice flow, right in the middle. And I never thought to put my bubble camera down there. I mean, it would have been quite hard for various reasons, but one thing I don't know is whether there are bubbles underneath the middle of the ice flow or just in the middle of the leads, because the ice is moving, the wind is moving the ice so quickly that there's basically a constant current under those leads. So it's not clear whether the bubbles appear just where there's open water or whether actually they're there under all the ice. And if I'd put my camera down that hole, I would know the answer to that question, but I don't.
Sounds like a good idea for the next one. I think that we have reached the end of our time. I don't know if Kai would like to say anything.
Well, I just want to say it's a fascinating talk. If it is not the most fascinating, but I can't think about anything else I have heard that has linked the climate change with the ocean, with pollution, with the and through the wonderful bubbles. So it's absolutely fascinating. I really want to move to this area to do some work. That's extremely inspiring. I have lots of questions to ask, but I'm aware that the time is up, and we also have the academic board meeting. So I guess we can stop here. But privately, I really want to ask you quite a lot of questions. Helen, be prepared. Thank you, and congratulations for giving the very first webinar.
Thank you for asking.
We have for this series. Thank you so much.
Thank you very much, Helen. It has been great having you, and thank you to all our audience. We hope to see you in our next webinar that will be in 2 or 3 weeks' time. Okay.
That's right.
Bye, everyone.
Thank you, everyone, for participating, and see you next time.